What Mivasana, and as I mentioned, we focus on the development of the material for energy applications. So we also focus on the development of energy storage materials, and there are two subgroups that study these materials. One is my own research group, and another one is Professor Varat Mivasana group. So we study the metal oxides for supercapacitors, and also other materials such as ferrite nanoparticles and carbon composite, and also biomass-based carbon nanostructure and composite as well. We have some guys who also study the first principles of these materials. Well, now let's move to the introduction about the energy storage. I think as for the previous talk by some of the speakers, for example, Professor Alan Drew, I think you have known about, and he also gave us some introduction about the energy storage material as well. I just want to make a quick overview of this again. So as you might know that the demanding on the new energy in the present day, we need to seek for some of the alternative energy as well. In this case, especially for my research group, I am interested in using the materials for energy storage devices. Why we are interested in this kind of materials? This is because the energy storage materials can give a very high energy density and high power density, and it also show a long lifetime with low cost, and also it is environmental friendly. So the materials will be used to fabricate the energy storage devices. These include capacitor, battery, supercapacitor, and also hydrogen storage. And for the talk today, we would like to focus on the application for a supercapacitor, and maybe we will try a little bit to apply it for battery as well. Excuse me. Okay, why we are interested in supercapacitor, as I just mentioned, is also maybe the same idea that a supercapacitor has high power, it has a long cycle life, and it can work at a wide range of temperature. And of course, this kind of device have a very high efficiency. So if we compare with a battery, I think supercapacitor have some advantage compared to batteries, as I just mentioned. And normally there are three types of a supercapacitor. The first one is the electrical double layer capacitor. The second one is the pseudo capacitor, and the third one is a combination of the first and the second one. We call the hybrid capacitor. So some of the materials can be used, or they show some of the properties of the three types of the supercapacitor. But what we try to use in my work, because the carbon that I will tell you later, that normally carbon will show the electric double layer behavior. But if we try to introduce some of the other materials that they also behave like a pseudo capacitor, for example, metal oxides or conducting polymer. So when we combine these two groups of materials, we can have the hybrid capacitors that also show both EDLC and also the pseudo capacitor behavior as well. So because this talk will focus on the carbon, activated carbon, so I would like to give you some introduction about activated carbon. These materials normally is this carbonaceous, highly porous, absorptive medium that has a complex structure composed of primarily of carbon atoms. The activated carbon can be produced by either physical or chemical activation from various types of carbonaceous materials, for example, wood or coal natural, etc. And what are the properties of the activated carbon? One thing that is very prominent for this material is this activated carbon has a large surface area up to 3,000 meters square per grams. It also have a porous structure, and the cost of this material is also very cheap. And well, as I mentioned, if you want to, because carbon show the EBR, okay, as I mentioned here, is the carbon will show the EDLC behavior, but we need some of the materials that show some of the pseudo-capacitor behavior so that we can combine them as a composite to have the hybrid capacitor. And the material of our interest is the metal oxide. For example, iron oxide, this material is low toxicity, is a natural abundance, and it's cheap as well. And also, for example, another one is the manganese oxide. This material is very interesting because it has high theoretical capacitance up to 1,300 farad per gram, and it is also low cost as well. So in our work, we try to fabricate the activated carbon from biomass, and some of the work we also try to use some of the secondary material, for example, metal oxide or other oxide to combine the two material for composite. Now let's move to biomass-based carbon materials. And the first one that I would like to introduce that we have done so far is the coconut shell derived carbon and composite. In these materials, we fabricate the composite and also the coconut-based carbon by using the pyrolysis. And for the composite, we use the hydrothermal. And for example, if I want to fabricate the composite between the activated carbon with iron oxide or manganese oxide, what I can do is try to use the activated carbon combined with iron sulfate in case of we want to use the iron oxide, right? And we do the hydrothermal process, and then at very low temperature, we can have the composite of activated carbon with the metal oxide of our choice. And in this work, we use iron oxide and also manganese oxide, and also combine both metal oxides to the composite system. After we obtain the products or the samples, we did the characterization using XYD, Raman as the techniques for checking the composition and also the phase structure of the sample. So from these two techniques, we can confirm the formation of carbon-based composite. And the Raman results show a very clear D and G peak of carbon. So we can confirm the formation of carbon by using Raman spectroscopy. And we also use the X-ray absorption spectroscopy to study the oxidation state and also the phase structure of our materials as well. And this one is the study of the carbon and also the carbon-iron composite. And the next one is the study of the carbon and manganese oxide composite. This is the morphology study by scanning electron microscope. This is the pure activated carbon. And this one is the morphology of the activated carbon from figure A, and for B is the iron with the carbon with iron oxide, and C is the carbon with manganese oxide. And for the D, figure D, we prepare the activated carbon with iron and also manganese oxide combined. TM, this one we can see the formation of the composite clearly. For example, in figure 11A, this one we can see the activated carbon. This is the pure one, and for the composite, we can observe the formation of iron oxide and also the manganese oxide, and this can be confirmed by the EDX technique. So next, we measure the electrochemical properties of the samples by using the electrochemical working station. So we also apply the 3 electrochemical cell techniques. And for the electrolyte, we use 6 molar of potassium hydroxide. And these are the results of the electrochemical properties. For the cyclic voltammetry or CV, we measure it at different scan rates, 220 and 200 millivolt per second. So at the low scan rate of 2, you can see that the dominant NE storage mechanism is the electrochemical storage. You can see the redox and oxidation peaks. And at the higher scan rate, for example, at the 200 millivolt per second, the dominant energy storage mechanism is the electrostatic storage. You can see the larger window from this figure. We also use the galvanostatic charge discharge technique, and we measure it at different current density, ranking from 1 to 30 ampere per gram. So the calculated specific capacitance is shown on this figure. And as you can see that we can have the carbon with quite acceptable value of specific capacitance. Interestingly, for the composite with pure iron and also the composite with pure manganese oxide on the red line and also the blue line, the value of the specific capacitance of this composite are lower than that of the pure carbon, as shown in the black one. But for the co-composite of iron oxide and manganese oxide, we can see the improvement on the specific capacitance, as you can see on the blue line. Okay. And if we do the Ragone plot to see the power density and also the energy density, and of course the performance of our sample, you can see most of the sample show the power density and also the energy density in this area, which means that the materials can be used as both battery and also capacitor, supercapacitor as well. Unfortunately, for the capacity retention study, as you can see from this figure, most of the material prepared show a very not so good the capacity retention, as you can see. But for the carbon, it's very good. Only the activated carbon composite with the manganese oxide show a very good capacity retention. So I think in the next step, we would like to improve this property so that the material can show a better capacity retention. Maybe we can apply to use the other composite phase, not just for the iron oxide or manganese oxide. Maybe other materials like glass, ceramics, or also some other complex ceramic oxide can be used as the reinforcement for the composite. Okay, now I think I have about 10 minutes left, right?
Yes.
Okay, I'll try to wrap it up. I go quickly. For the second one, we also study the cassava root derived carbon materials. And for these materials, because in Thailand there are many cassava farms, especially in our near our campus in the northeastern of Thailand. The farmer, they grow a lot of cassava. So I think it would be a good idea that we try to use the cassava root as the derived carbon-based materials. So in this work, we try to apply to use two activated materials. The first one, we use the sodium hydroxide. And for the second part, which I will tell you later on, we use the potassium hydroxide as the activated materials. For the first one, this is the result of the carbon derived from cassava, and we use the sodium hydroxide as the activated materials. And for the preparation, we start with, we try to use the cassava root. We cut it off to small pieces, and then we dry it. And then we first carbonize it at 400 degrees Celsius. And at this temperature, we mix it with sodium hydroxide about the ratio is 1 to 3. And we do the carbonization at high temperature. And in this work, we use 600, 700, and 800 degrees Celsius. So after this, we can obtain the activated carbon. The color is in black, of course. And we also do the basic characterization using the XRD, FT-IR, Raman spectroscopy, SEM, and also other techniques as well. As you can see from the SEM image, that we can see the structure of the product structure of the cassava-derived carbon. And we also use the X-ray photo electron spectroscopy at the synchrotron facility to study the oxidation state and also some chemical composition of the prepared products as well. And for the electrochemical properties, we also do the same measurement. We use the CV and also the GCD techniques to evaluate the electrochemical properties. And this one, we can calculate the specific capacitance. The highest specific capacitance is observed on the sample prepared at 700 degrees Celsius, which have the specific capacitance of about 128 farad per gram at 0.5 ampere per gram. And as you can see from this figure, that at 700 degrees Celsius is the best condition. And so we try to sort it out why this temperature is the best condition for the preparation of the carbon-based material that give the highest specific capacitance. And one of my students also tried to use the prepared material for the fabrication of a simple model fan or small white wind turbine, and it works. So this confirmed that this activated carbon electrode from cassava root can be a potential candidate for energy storage application. And for the second work, as I mentioned, we try to use the potassium hydroxide as the activated agent. And the process, we also do the same for the preparation of the carbon. And these are the SEM images of the sample we prepare. And we study the electrochemical properties. But this time, as you can see from the SEM image, you can guess that because the porous is quite small, even smaller than the previous work. So we expect that we would get a better electrochemical performance. And as expected, that we can obtain the high specific capacitance up to 175 farad per gram at 200 at 2 ampere per gram. And we also try to increase this value by introduce some of the potassium manganate to the system, because there is some paper that when they mix of the potassium hydroxide and also the potassium manganate to activate the carbon, so we get a better performance of the electrochemical properties. So we follow that concept, and we get a very good result, as I will show you later. And this one, you can see when we introduce the potassium manganate to the system, so the value of the specific capacitance increased. For example, this one from 69 farad per gram can be higher up to 341. You see, there is a big improvement of the specific capacitance from this preparation method. Okay, now let's move to probably the last one, because I'm running out of time. I think I just show you the tamarind wood derived carbon. I think in Indonesia you also have the tamarind wood, right? So because in Thailand we also grow a lot of tamarind, and so one of my postdoc, he want to try, so he prepare the tamarind wood derived carbon. Of course, we use the carbonization process, and we use the phosphoric acid as the activated agent, and we also study the basic characterization as we have done before, as on the other materials. So for the Raman spectroscopy, this also confirmed the formation of the carbon of the material prepared from tamarind wood. And these are the electrochemical properties. We obtain the value of about 60 farad per gram from these samples. And this is just the beginning of our study, so we try to improve the specific capacitance of this material by introduce the composite concept later on. But this one is just the first batch of our study. We also try to prepare the coil cell to see if we can make some the real supercapacitor or battery, and this show that we can fabricate the coil cell by using the tamarind wood derived carbon, and it show a very good properties. So in the next step, we will try to use the concept of composite, as I mentioned, to improve the electrochemical properties of our composite. Last one, maybe just quickly show you some of the Mangosteen pure derived carbon composite. So everyone know Mangosteen. In Thailand is we call it's the queen of Thai fruit, right? For the durian is the king of the Thai fruit, and I'm sure that Mangosteen is also available in Indonesia as well. So in Thailand we have a lot of Mangosteen, especially this time, and durian as well. So we have to eat both durian first, and then we follow up by using Mangosteen. I don't know, it's a logic of the old people. They told us, so it works. If you eat just durian or mangosteen, you might have some problem with your stomach and you might get sick or something like that. Okay, anyway, we use it for preparation of the carbon materials. And again, we use the carbonization process. And these are the morphology of the mangosteen pure derived carbon using the scanning electron microscope. You can see a lot of porous structure on these samples. And for the electrochemical properties, you can see very interesting point that we can obtain, I think it is acceptable value for the specific capacitance. The highest value is up to about 160 farad per gram. So this material is abundant. So I'm sure that if we maybe ask Prof. Andrew show us before that we can develop it to use as the sodium batteries or a supercapacitor. So the raw material is very cheap and we can find it everywhere. So I think I will finish with this slide that we also have some project that we get the funding from research network on nanotechnology project supported by nanotech and also our university SUT. So actually Professor Varat Nivasana also have he setting up his own company now to run on the energy storage products. And we also use some of the material that I just mentioned in this talk to fabricate some of the supercapacitors. And maybe in the near future, I will show you of our progress on this research. Okay, the last one, before I finish my talk, I would like to invite you all to attend some of the conference that the Material Research Society in conjunction with Chulalongkorn University, Suratnari University, and MTech. We organized the AMF EMIC 2021. This will be taking place next month on the 6th to the 9th of July. The conference is fully online, so the registration fee is quite cheap. So if you are interested in joining us, please join us. And I look forward to seeing you all at the MF EMIC. Thank you very much. Thank you.